7th monthly seminar, which is part of 12 months, 12 seminar series by SPG Emerging Technology. So as you all are aware, today's topic is Industry 4.0 Data Centric Way. When you must have noticed that as soon as you enter any Industry 4.0 compliant factory, you start experiencing the future of manufacturing. For example, mini data centers store critical sites data locally, allowing greater accessibility and security controls. All USB keys must pass through the decontamination terminals, and sensors monitor machinery to predict instead of reacting to maintenance needs. So, moreover, augmented reality accelerate operations and maintenance, resulting in productivity gains, while energy innovations achieve power savings. This digital factory not only showcases the benefit of embracing smart technology, but also the ease at which any business can begin its own digital journey. So to take us through this very interesting transformation, which is happening very fast globally, we have Atul Marathe, who is JPP alumni of 1976 Junior College batch. He did his BTech from IIT Bombay in '82 and postgraduate diploma in industrial engineering from NITI in 1984. He has worked in software product and services companies in varied roles for over 30 years. Currently, he is learning and teaching new technologies to mentor and guide engineering students to make a good career. He is advisor and trainer at Center for Industry 4.0 Pune, for whom he has developed an Industry 4.0 maturity model for MSMEs to create their digital roadmap. Today, he will introduce us to Industry 4.0 concepts in his own founded unique data-centric way, not found in literature. Hope you find it interesting and enjoyable. So before handing over to Atul, a standard request to keep yourself on mute during presentation. You may put your questions in chat box, which Atul would try to address during his presentation, or if not covered, certainly during question and answer session, which will be after presentation. Yeah. So without any further delay, I welcome Atul to take us through this session. So
as you said, today we will cover Industry 4.0 in a slightly different way. That is the data-centric way, and therefore for their maturity model project, because they wanted to have some way of small companies also. And then we would like to push the concepts through the simple model first. So, and the second part I find is Industry 4.0 as a historical evolution also. It is more evolution of computer science, I would say, than manufacturing. So there are some people who doubt whether it is manufacturing, whether it is computer science, or what exactly it is. But as we know today, most of the things are artificial intelligence controlled, and that is more of computer science than human brain controlled. So we will look at it from a data-centric point of view, which I have evolved as a methodology of learning. Secondly, I'm personally interested in a lot of experimentation on the learning techniques itself. So you will find that all these Zoom-based meetings in the pandemic we are becoming expert in that. And to take it one step forward, I always suggest even to the students whom I mentor that don't rely on me as a teacher. You should rely on available literature. You should rely on Google. You should rely on videos. You can rely on a lot of stuff which is available. And I'm trying to create an online course also, which is sort of automated. So in today's session, we will like to go through it in that style, provided we successfully do it, so that I will talk less and maybe show you a few videos. Some of them are YouTube videos, which talk a lot about Industry 4.0. And there's one video which I'm creating with a company in Bombay called NeoEd Education. And that's a course on Industry 4.0, which is supposed to go completely online. So I will give you a glimpse of that also, that how we can explain some of the concepts through a video. Then after that, we will see this data centric approach, that what is this unique approach which is not there in the books or in the literature. And lastly, the dream is to create a digital twin. So obviously we need to understand what is a digital twin. That is the final vision of Industry 4.0. It's already documented very well, and you can find a lot of literature on digital twin. And whether you want to reach that ideal or don't want to reach that ideal is a separate issue, because there are lots of fights over people losing jobs because of automation and so on. So those who are in great favor of automation, they might say digital twins is great. But there are some others who might say, no, we don't want to come to that level of digital twin where everything is automatic. But we would like to have all the controls with human beings. So that I will leave it to you, to what level you would like to implement the Industry 4.0. It's not necessary that everybody has to create everything automated fully, but it looks like that's the way the world is going. So with that, let me start with a presentation. It will be a little, not too long, but given our time, maybe an hour or so. And I will like to show you several videos as a part of that presentation also. So you may need to, I may need to change the screens a little bit in between multiple times. So I hope the first screen is visible to you now, the
Yeah,
presentation.
it's visible. No
Yeah.
problem.
So let me make it a little bit bigger for me to understand what it, yeah. So Industry 4.0 is the fourth industrial revolution that people are talking about. I hope the slide has changed on your screen, because sometimes it doesn't.
Yeah.
So it's a term that has been coined around 2010 or so, I would say, or a little bit later after that. And this is a German name, Industry 4.0. Americans don't like to call it that way. They call it smart manufacturing. But most of the lead in Industry 4.0 is taken by 3 or 4 companies in the world. One is Siemens, of course, other is Bosch, then there's GE Electric, and there's IBM. So these are the 4 or 5 companies who have taken lots of initiatives. And so whether it should be called the German name or it should be the American name is a different issue. But yes, there are 4 levels of industry automation that were thought of as a afterthought in these years. And that's where we started talking of industry revolution 1, 2, 3, and 4. So instead of telling you again more details, I would suggest we can have a short video. That's the link here, the 6-minute Siemens video. So let's see that.
Tomorrow's manufacturing. Products finding their way independently through the production process. In intelligent factories, machines and products communicate with each other, cooperatively driving production. Raw materials and machines are interconnected within an Internet of Things. The objective, highly flexible, individualized, and resource-friendly mass production. That is the vision for the fourth industrial revolution. A look back at history. At the end of the 18th century, the first steam engines and the intelligent use of hydropower revolutionized production. The late 19th century saw the rise of electrical engineering and mass production. The first moving belt conveyor was used as long ago as 1870 in the slaughterhouses of Cincinnati, Ohio. In the mid-1970s, electronics and IT began to expand rapidly into industry. Siemens developed the first SIMATIC. Production became increasingly based on computer-assisted controls. The fourth industrial revolution is still a vision. Experts believe that it will only become a reality within the next 20 years. In intelligent factories, everything is interconnected wirelessly. At the German Research Center for Artificial Intelligence in Kaiserslautern, this future can already be experienced right now. Research is underway here into exactly what the industrial production of tomorrow will be like.
Fabriken werden zukünftig aus Bausteinen bestehen, aus smarten oder intelligenten Bausteinen, wie man es nennen mag. Vergleichen wir das vielleicht mal so ein bisschen mit einer Lego-Steinwelt. Das heißt, wir haben standardisierte Bausteine, die wir hoffentlich relativ einfach zusammenstecken und zusammensetzen können. Jeder dieser Bausteine hat bestimmte Funktionalitäten und wir können sie zukünftig in einem solchen fabrikinternen Internet dann kombinieren.
A bottling plant for liquids, set up together with Siemens, is used to demonstrate the most important components of the intelligent factory of the future. Each bottle contains an RFID chip storing a precise description of how it has to be processed. Which liquid, which lid, and which label. At each station, the bottle communicates directly with the machine, telling it how it has to be processed. At the end, a computer checks whether the bottle has actually been produced as desired. Factories with networked machines and products are already in existence today. In the future, however, these hitherto self-contained systems will be connected together in a comprehensive network. All devices, machines, and materials will be duly equipped with sensors and communications technology and connect to each other. These systems are known as cyber-physical systems. The highlight is that they communicate with each other and also control each other cooperatively.
Wenn Sie sich das Thema Industrie 4.0 angucken, dann basiert sie ja auf der Logik dieser Cyber-Physical Systems. Das heißt, Sie haben autokrate selbst arbeitende Systeme, die sich optimieren und sich gegenseitig austauschen und dadurch letzten Endes Produktion optimieren.
Ja, die Vision sieht so aus, dass wir ein Internet quasi hinunterziehen bis auf die unterste Ebene. Das heißt, jeder Sensor, jeder Aktor wäre damit quasi ein Teilnehmer eines Internet der Dinge. Jedes Gerät hat damit eine eigene IP-Adresse, ist damit adressierbar in diesem Netzwerk.
For the customers, this means tailor-made products at relatively affordable prices. For industry, it means highly flexible mass production that can be rapidly adapted to market changes, because in the future, product life cycles will be even shorter. Another reason why it's increasingly important to depict engineering across the entire life cycle. Maintenance, for instance, is planned in from the very start.
Wir haben ja bereits in den 90er Jahren mit Totally Integrated Automation entsprechend ein Setup gewählt, wo unsere Produkte und Systeme sehr gut miteinander kommunizieren können.
At Corporate Technology in Princeton, a cyber-physical control is being researched even today. The vision, the control, and all linked sensors are connected to the internet.
One potential scenario is enabling the PLC to react to utility pricing information in building automation. We can enhance PLCs to use simulation to calculate how much to pre-cool a building, with the ultimate goal of turning off the cooling system during peak times.
But that's just the beginning.
We've prototyped capabilities in the PLC to access big data in cyberspace in real time. And we've also enabled a network of PLCs to connect to a dynamic simulation of the entire physical process.
Siemens is shaping the future of industry. Connecting the real with the virtual world of production is making it possible to enter entirely new dimensions in quality, efficiency, and flexibility. The company is well prepared for Industry 4.0.
So friends, you'll realize that this video was from 2013. So it was almost 8 years old, and they talked of
Good
some
grammar and spelling
vision.
are important.
Sorry.
But if you want to write essays that
Just a
inspire,
minute.
messages that forge brighter connections,
1 minute.
and emails that get the job done, you need to think about more than just grammar and spelling.
Visible now. So this is what we saw as the history of industrial revolution. And as a learning aid also, you can realize that either I could have talked all about this, or you could have seen a video, and then I can sit and relax while you understand it much better than what I would be able to explain you, how the industrial revolution, or 1, 2, 3, etc. Okay, so looking at it slightly differently, if you look at it more technically, then there are different kinds of skills or different kinds of applications that were developed for Industry 4.0. And this map, basically, which is developed or taken from C4I4, they say how India is progressing against Germany, for example. So what Germany did in 1910, that's the timeline you see at the bottom. So there are different kind of applications like 1, 2, 3, 4, 5, 6. This is the sequence they went ahead with. They started with in 1910 and we started in 1950s. Then whatever Germany could achieve by 2000, we achieved till 2015. So you can see how all this spreads across the world at a much faster pace today. And then whatever Germany is already done by 2020, we are yet to reach there. So the red part of it, you'll find some of the applications or some of the areas where a lot of developed countries have already reached there while we are not there. So it will be maybe another 2 or 3 years that we will catch up with them, because that big gap of 40 years will now come down to 4 years, maybe by 2030 or something. So that's how we are going fast. And there are different applications, you can say, basically starting with individual skills, going to use of IT tools, collaboration among these IT tools, and lastly, the smart manufacturing part of it. So that's how this evolution is going on. I would not like to get into all these, but we will see some of the things of which are there in red, which is the new, I would say, new skills or something we can say for learning industry 4.0. Those are the skill sets. So if you try to look at it, that what's happening in the past and what's happening now, some of us will be surprised to know that in 2006, that is hardly 15 years before today, all these things did not exist. And if you ask the children today, how, then they will say, how did you survive in the world without all these things? So that's how the changes are there. It might be interesting to just have a look at this list, that all these things were simply not there in existence in 2006, just 15 years ago. And that's how rapidly the technology keeps changing. So let us move or shift our gear to what is this changes in terms of industry 4.0. These are all generic changes that affect our everyday life. And similarly, for the industry as well, the industry 4.0 has a certain set of things that affect their life. So the accelerators for industry 4.0 are all these, which you see here. What I have done is, for this, I would like to show you a short video of the course that I have created for this industry 4.0, that online course. So there is a functional industry engine. And besides that, there are many things like you need IoT platforms. So these are something like what are the additional things that we have done in the recent past towards industry 4.0 to really call it industry 4.0. And the industry needs to adopt all these things. All these are being adopted in certain levels, I would say, not zero for everything. But in India, yes, if you look at the small and medium scale industry, they are at different levels. Some of them adopt certain things. Some of them are simply not aware of what these things are, or some of them only know it as a theory, but don't implement it. So IoT platform is one, big data analytics is another, cloud computing is the third, cyber security is the fourth, advanced robotics is one more, simulation, system integration, additive manufacturing. This is something which I doubt whether it should be called as industry 4.0, because that's a process methodology. It's not a technology similar to the other technologies, but a slightly different kind of technology. But many people in literature include it, hence I have also included it here. And lastly, we have augmented reality or virtual reality. So these are the different things which are the key technology elements of industry 4.0. And let us have a look at some of them, because I don't think that I would like to tell you in detail of each of them, but I would like to give you a glimpse of how this course has been created, where we are explaining some of these things online. So just let me share that screen to show you this course content, which talks of some of these technologies. I hope you are able to see this screen as well.
Welcome to the course, Industry 4.0. The course will be conducted online during the period 15th of December 2020
Yeah, let
to
me
30th
skip
of
some of
December
it.
with an objective of finding ways to strengthen manufacturing quality and energize the workforce towards it.
What I will do is I'll go to the part where we talk of these modules and not the other part of the course.
And desire to reach a maturity level in a foreseeable future.
So it will help us understand these modules and not the other part of the course. So
Major technologies
here.
that can be used to achieve the desired objectives. This could be a bit overwhelming for those who are venturing into this domain. In addition, there are more industry-specific technologies. In this section, we will list most of these technologies, which are commonly used, so that the participants get an idea of which technologies could be more relevant to them. Learning so many technologies is like embarking on a long journey. An organization may not focus on all of these technologies. They will have their own priorities to implement some of these in a logical sequence. The selection of technologies is made depending on what stage the organization is currently, what are the pain points, and what they want to achieve. The diagram shows a list of many such technologies, important and relevant to Industry 4.0. This, however, is not an exhaustive list. Some of the technologies or software tools are not listed here, as they form a part of Industry 2.0 or 3.0. For example, ERP, SCM, PLM, etc. A factory unit has several assets like machines, equipment used for inspection, transportation, air handling, besides tooling, jigs and fixtures, etc. These assets are used in manufacturing process steps that create production data and also create their own usage data for maintenance purpose. This data is available at the asset or equipment level and needs to be made available for other users and computer applications. An Internet of Things, IoT, platform enables one to connect all these assets on a network. Thereafter, the required data is transferred from an asset to central servers or cloud infrastructure. This is shared on a need basis. Similarly, there can be decisions taken at the higher level that need to reach back to the machines to act on. This can be done either manually or automated for robotic operations. The IoT platform is also used to receive this data back from central or cloud system and then transfer it to the equipment level. Usually, the IoT systems transfer data between machines and an edge computer, which in turn is connected to the Internet cloud service. This is done to avoid and limit the number of machines which are directly connected on the Internet. Edge computing also helps in transferring business decisions into a format that is understandable by machines for taking automated actions. We will cover IoT in more details in this course as part of data capture. The cloud infrastructure enables an organization to seamlessly access and share data across multiple locations. Amazon AWS and Microsoft Azure are commonly used cloud platforms. The cloud computing infrastructure has eliminated the need of having organizations own central servers that connect to edge computers. Later, during the course, we will have only a passing reference to this technology as part of data aggregation and collation steps. Details of how to set up and use cloud infrastructure will be a separate standalone learning topic. Every organization has business critical information assets like data, applications, network, servers, PCs and machine control systems. These need to be protected from threats like hackers and computer viruses. Unprotected computers and devices, if hit by malicious programs can disrupt production for several days. Also, there is a risk of companies' sensitive data falling into the hands of hackers or competitors. Cybersecurity technology protects an organization's information assets from such threats. Cybersecurity ensures the confidentiality, integrity, and availability of data and devices and ensure smooth operations. This is a technology that has existed for long, since the advent of networked computers. However, the focus has now shifted to enhanced security of data, which is shared across machines over the network by IoT-enabled equipment or edge computers. This is also a separate, standalone learning topic in this course. Robotics
Okay,
play a
so
vital role
let me
in
skip through some of these
automating
because
actions
there are
on
many
any
such
workstation.
modules which you saw there,
Robots
and we'll come
need
to
receive decisions
the
as
system
digital
integration
data.
part of it.
This requires a broad knowledge across technologies to be used with a clear business focus on the outcome to be achieved by this integration. The system integrators also need to negotiate and collaborate with various technology providers. They need to achieve a common goal for an organization, reaping benefits from integration of several technologies. The case study approach in this course will help participants to get a good overview of how to identify projects that work across technologies and work towards a common Industry 4.0 objective for an organization. We will also see how few technologies evolved in the past as three pillars that need to be integrated to deliver the promised goal of Industry 4.0. System integration skills, though not covered in detail, will be required to implement these projects. We talked about data collection in IoT and data aggregation and collation in cloud computing. These are the two key focus areas for this course. The third important focus area is data intelligence. Data analytics is the technology used to make sense out of the relevant data, which is collected and collated. This information is then used to take data-based informed decisions. We will cover this in detail in our course, as this is the latest and most important step in Industry 4.0, that is, to put the available data to use in predicting and prescribing actions. Additive manufacturing, also known as 3D printing, is a specific technology that helps a great deal in producing parts on demand, using a digital design as an input. Creating digital designs to produce parts using 3D printing is outside the scope of this course. Simulation is a technology used in Industry 4.0 to do a what-if analysis for different scenarios in production planning and routing. There are software tools available to do design simulation as well as production simulation. We will briefly cover it as part of digital twins as a goal for Industry 4.0. However, the details of simulation software is outside the scope of this course. With a lot of gaming and visual simulation software available, industry can make use of this technology for two objectives. First is virtual reality. The virtual reality tools help do simulations of real situations to do a what-if analysis. It is also a good tool for training and helps getting clarity in concepts. Second is augmented reality. The augmented reality tools help in doing a job much better and safer by having visual aids to assist the operator in his or her role. It can provide additional views or insights to the job at hand, or a close-up or enlarged view to take better decisions. We will not be covering this topic in detail in this course. Thank you for going through this chapter on technologies in use for Industry 4.0.
Okay, friends. So that was a glimpse of what an online learning course could be. And this is something which I have created with my friend at Mumbai who creates online learning courses. So I find it quite challenging and it takes a long time to create such kind of courses. But I hope that you get an idea that how we can start creating a course on Industry 4.0, then what are the various modules that we saw in that. And you also saw in this video that we are saying that a lot of these modules will not be covered as a part of the course. So doing a course on Industry 4.0 and understanding all these technologies is really a challenge. And that's why people find it quite difficult or sometimes really quite mind-boggling to where to start on all this journey, because there are too many things to be looked into it. So before going ahead, I would like to take a short pause if there are any questions or if anybody would like to discuss any about this, what we have covered. Otherwise, in this analytics, we saw that there are the three pillars, and we'll talk of those three pillars briefly before going to digital twins.
I just have a small question about employability and employment. You mentioned about fears people have. So has any study been done to find out how many jobs would be lost and how many jobs would be gained? Because the general argument is that the nature of the jobs will change. There will be no job losses as such, but the nature of the jobs will change. The competence levels required will change. So has anyone really done let's say to make a motor, for example, like Siemens does? With this, if there are 4 jobs being lost and 10 jobs being gained, then yes, there is a net gain of jobs. But without this kind of study, the statement doesn't seem to be very convincing that jobs will not be lost.
No, there are existing jobs which will definitely be lost. But I find that most of the jobs which are created today are also because of technology. Isn't it true? If the computerization was not there, there were a lot of jobs which were manually done. And with the advent of computers, right from banking to
number of jobs,
that jobs are not there.
No, I'm talking about number of jobs. Let's say 4 jobs are lost and 6 are created, understandable. But if 6 are lost and only 3 are created, then that's a worrisome factor.
No, I never think that that is a truth in life. There is always something and enough things that can be done in life. And it only depends on what skills are required to do those things which are of value now. So something that has a value in the past doesn't have a value now, and whatever has a value in the future, people don't know it now. So I don't think that there is any dearth of less number of jobs being there or something. But yes, overall, if you talk of abundance mentality in the world, you'll realize that the kind of production and the kind of outputs that could be available in the world, and if they are really distributed equitably, then the biggest problem mankind will face is how to spare their free time, because you'll have a lot of entertainment to do yourself, because everything will be free and available to you. And this basic minimum income scheme, which a lot of countries are talking about, that you don't have to earn for a minimum living. Just you want to live, eat and sleep, you don't need to earn at all or don't need to work at all. So that's another way of looking at life. And there are a lot of countries who are saying that their income levels or the wealth that the countries have is almost that much that the whole world can sit and do that without working. So I don't have these numbers or figures, but yes, if you look at LinkedIn, there are some surveys which are done, and there are some literature available, which I might have to hunt and find out that which are the jobs which will be lost in the next 10 years and which are the jobs which will get created in the next 10 years. There are some surveys done in that, although without numbers. But the skill type, for example, if you are a data entry operator today, then obviously that job is likely to be lost in the future, because you won't need so many data entry operators with all IoT devices. Secondly, if you are a truck driver today or a bus driver or a taxi driver, then you can say that yes, these jobs are not going to be there because of autonomous vehicles coming in. So there are some jobs which are obviously not going to be there. And if you stick to those jobs saying that, no, I want this job because I have this skill only, then it's going to be a challenge for them.
Thank you.
Atul, a related question. Industry 4.0 seems to be very technology intensive.
Yes.
How is industry taking it? I mean, what is the either IT technology or all these computers related technology capability of industries in India and across the world also? I mean, you can answer it later if you're going to cover it later or some aspect of it. I just wanted to ask, how is industry looking at it?
No, this session doesn't cover that, so I need to answer it right now. So the way it works is that there are some MNCs and bigger companies in the world who realize the benefits of automation and they want to do it. So they will push it down to their suppliers and that will come down to the further level of suppliers. So in implementing Industry 4.0 cannot be done standalone in one company. That's for sure. You have to look at the entire supply chain from your customers to the suppliers, and it is mostly driven by the customers because we are the people who say no, I want it right now, I want it in 5 minutes, I want it in 10 minutes, I want it customized, and if you are not giving me, I'll go to somebody else who does it. So if you are willing to listen to these customer voices and willing to change, that's the only way you can do it. And Industry 4.0 is one of the ways of doing it, where I say that the simple mantra that people are looking for today is cheaper, faster, and better. Earlier, we were looking for better, then in between, we are looking for cheaper, and now we are looking for faster, and we are looking for all these three. So with the passage of time, the expectations of the customer keep increasing. So earlier it was only better because when there was no technology, people wanted to have things which are better than what they could do manually. And then they said, oh, better is acha ho gaya. Now I want it faster because there's a lot of demand for it. And then now we want it even customized and we want it faster, better, and cheaper. All of them are together. So all these MNCs will definitely drive it. And then we have to see that who others survive and who don't survive.
Right. So as you said, 2030 could be the timeline for Indian industry. A lot of it are to kind of accept and get to Industry 4.0.
No, I always say that don't look at India as a follower for everybody now. We are already a bigger country and we should be starting looking at where we can take the lead. So if we have all great computer scientists in India, why don't they look at this data intelligence and AI based technology to use all this? Why should we follow the world?
Sure.
If we can always build this technology, if Indian companies don't want to use it, you can always export this technology because it's all software and it can work with other companies. So you can be expert at that. It's not necessary that Indian companies need to really switch and change till they are forced to change. So there's no need of pushing somebody to change. You will automatically change because everybody understands how to remain in business. I don't think all industries are smart. They know when to remain and how to remain in business. Right?
Sure. Thank you.
Atul, the slide which talked about accelerators,
Yeah.
right? So most of the accelerators are actually, I would say, are not just accelerators, but they are basic needed components of Industry 4.0. Like if IoT is there, then only it can work. Then data analytics is like whatever data collected will be used. So from, as you rightly said, if it is they want cheaper, so cloud computing is required. If whatever data is huge data is collected, if that needs to be processed and analyzed, then only it will give results. So big data and AI and ML will come. So all these things are just not accelerators, but it is actually basic needs of Industry 4.0 to be successful. Am I right in saying so?
Prashant, I would put it this way. We saw a slide before that which said that what was not there in 2006. Okay. So if you had asked a person at 2006, do you need all these technologies without which you cannot survive? He will say, no, these are all stupid things. We don't need it. And if you ask a person today that can you survive without it, they say, no, they are basic needs. So that's how you're putting it.
Right. So industry
correctly, that all these are supposedly basic needs. But
for Industry 4.0 to be successful, these are basic needs.
Yes. So
Industry
these
4.0 is it required? It may not be, as
Yes.
you rightly said. Yeah.
So it's a hint that what you should be learning because people are
Yeah.
saying we need to reach,
Right.
we need to do this. So that's okay. Let's come to that slide also. I'll just
Yeah.
start. So we come back to our presentation and I'll show you what exactly are those the things that we are talking about. So these are the accelerators or technologies that people need to learn. And see, these are the reskilling challenges if you ask. So to learn these technologies, you have to understand how to do complex problem solving, critical thinking, creativity, because you are trying to move from what you're doing right now to a different way of doing things. So I would say, yes, technology is definitely there, but this attitude is a bigger problem of switching to technologies. Once you have the attitude and the motivation, then the technology follows. So these are the new, I would say they are not nothing new in this, but this is all the reskilling challenges that people need to think creatively. They need to understand what is to be done, how it can be done. You need emotional intelligence, service orientation, cognitive flexibility, and that's all. These are basic skills, I would say, which changes your attitude towards thinking and towards learning. The earlier slide which we saw was the skills. So those were the different skills. These are technologies, yes. But to learn these technologies, you need to do this. And that is where we are saying that, see, earlier there was another way of looking at it, that people say that forget about all these new technologies, what do I do with what I have today? So there's a functional way of looking at it. If you look at a SAP screen, for example, which I'm sharing right now, so this says that how a manufacturing works is represented in SAP this way. I remember that when I passed BTech in 82, and this was my topic of interest, MRP systems, because my BTech project was also around this. So when I used to go to factory and talk to people about such things, they used to say, why are you doing all this in one place? There are so many departments, there are so many different skills. Do you expect one fellow to know all this? It's impossible. And they said all this ERP, etc. will not work because, all these departments are separate. Production is different, sales is different, marketing is different. How can all of them could come together and try to share something? They have their own way of sharing through people, and those people are expert, and you can't expect one person to be expert in all this that you think is an ERP system. So today we don't believe that way, but we believe everything can be done together. So it could be a time when we say that the future generation kids will say that all these technologies for industry 4 is like, yeah, everybody knows all those technologies. What is so great about them? We know all of them. Today we might find it really challenging that how can we learn so many things together? That's how I would put it. That's why I put this chart also, that this is an old chart from SAP 1980s. And people thought, ये सब sapne karna, it's almost impossible, like somebody trying to understand all this together. Same is there for industry 4.0 today. So earlier we had all these applications. If you look at it, a slight history that how these functional software applications came to use, that is industry 3.0. So the basic objective of these applications was the ability to store and integrate digital data, which was received from various devices on machines or otherwise from different computer applications. These applications had this kind of expectations that you should have rule-based generation of triggers, alerts, warnings for manual action, and or IoT-based machine action, because sometimes PLCs and those kinds of things were used earlier also. Then we used to analyze historical data trends, external data for improvement and prediction of any preventive or preemptive actions that could be taken, and real-time responses and changes, and some simulation models for foreseeing the changes. So all this was possible using these tools of the 1980s, I would say. Most of these tools had been started from 70s and they matured till 2000, and all of them are available today. So we don't talk too much of these tools, but yes, we do need to talk of IoT and data analytics, and which are the relatively new tools, I would say, which are used in industry 4. But these tools do exist and they will continue to exist in a different format. Okay, so coming to those 3 pillars that we were talking about, that how we can look at industry 4.0, not from a 10 technology perspective, which is a bit daunting. I put it this way, that there are 3 basic pillars for industry 4, which is a slab on top. And if you want to implement this slab, you need the 3 columns in place. If you look at a civil engineering point of view. So the 3 columns in place are, one is how you collect data. That is the business applications of ERP SCM, which started in 1980s. That column started first. The second column is 1995 it started, that is IoT, IIoT, and how do you capture data directly at the machine level rather than trying to do a data entry through manual forms, etc. And in 2010, we started with analytics and AI-based decision-making solutions. So you could call these 3 columns as see, think, and do. So what Industry 4.0 does is it automates this process of seeing, thinking, and doing, which is already being evolved as different technologies. And all we are trying to do is integrate the three. So a very short quiz for you. Which of these three columns are see, think, and do? Can you identify? Which is the first one? The business applications column. Yes,
Think.
anyone? I'm not able to see the other screen.
Is that the think column?
So which is the C column, which is the think column, and which is the do column?
The middle one is the C. First is think. Last is
Do. Perfect. Because based on AI, you can actually implement it. So this is the technique that I have evolved, saying that if you want to understand and learn Industry 4.0, look at it from a data-centric view and look at how these three columns can be the foundation, called the data foundation for Industry 4.0. Now let's see how this data foundation can be done in an industry, because this is a conceptual level of how three pillars can build it on top. And why we need to do this now, there are another reason that people say that, fine, if you want to implement this, where is my ROI? What is the KPI? What parameters I should monitor, and so on and so forth. That's the next question, that how do I know I'm progressing or not progressing? And we find that most of these things are done by engineers, not by finance people. So I find that as another challenge, that all engineers, they don't like this idea of finding out कि ये सब क्या चल रहा है on financial terms, कि what is the ROI, what is the payback period, etc., etc. So I tell, forget that. The simple way that which I suggested for C4I4 is look at 4 latencies to reduce, and every technology person understands it, who is zero in finance. So the first is, as soon as an event is happening in the factory, what is my insight latency? That is, how long does it take my systems to know that this event occurred? The next step is the data aggregation latency. So how long does it take for me to get the relevant data to take any decision based on this event? For example, a machine is, let's say a machine breaks down. It is working and it just stops working. So I need to know what happened first to take action. Then the next action I need to know is I need relevant data, that what is this machine, what it was doing, which job is getting pending now, which new jobs are there, which were supposed to be loaded on this machine, then what is the maintenance cycle of this machine, where are the spare parts of this machine, and so on and so forth. So you need a lot of data to be collected first to start acting on that machine. And then you need a decision latency, that with all this data, you need to make a decision that what exactly you want to do, whether you want to repair that machine, whether you want to replace that machine temporarily, or you want to divert these jobs to other machines, and whatever. So there could be different actions that you can take while this machine is under repairs or it's not working. And lastly, all these decisions need to be conveyed back into certain actions. So you need to create action items from these decisions that you take. So there are simple 4 latencies that you can think of for the entire gamut. That, and if you look at the uh, list below, which is in different colors, the first latency is addressed by capturing data by IoT. So the event insight latency can reduce. The collate part of it, like the relevant ERP data and all those other business applications, they get you the data fast, what you need. The conclude part of it is based on AI ML engines. So if you use modeling tools, they can take decisions much faster. And lastly, again, the action can be automated by controls by digitally through IoT and AR, that is augmented reality. So if you look at 3 pillars and if you look at 4 latencies, that's the model I'm suggesting, which is not there in the books, that what is the simplest way to understand Industry 4.0 and what to focus on. So everybody in the factory can look at these 3 things. What are those 3 basic data elements that I need to have in the factory, and what I am trying to reduce as the objective. So if you reduce all this using the data-driven approach or the data-centric approach, then you will be almost close to Industry 4.0, and we'll see what is that digital twin that we talk about very soon. So in one picture, if you want to put all this, you will see that there are these 3 colors that you see here. There is certain things in blue, certain things in red, and something in green. The green part is what is more related to data capture. So it's close to the machine. So from the machine, data goes to the edge computers, and from there, there can be certain control actions directly on the machine. So that's the shortest loop. If that is not enough, then this edge computing data needs to go to the cloud computing or the central servers, where you need application data, you need external data, So all this in red is the second column, the ERP and those kind of business application data. So that also is required. And then this blue is the decision making part, which could be either manual decisions, or you could do simulations, or you could do AI based predictive analytics, or you could do prescriptive recommendations directly. And all these result back into some actions through the edge computer on the machine. So they could be, again, actions could be manual, it could be directly closed loop at the machine level, it could be based on all this intelligent decision that you take here, or it could be manual through the other business applications. So this is the data focus that I discussed about Industry 4.0, that you have to look at these three colors and see which one you want to grow on, or which is lacking in your organization and what you want to be making it stronger. But all these three colors need to work together to complete this cycle. So the data foundation part of it, the more details of it, if you want to know, then yes, what comes from edge computing is the real-time machine data summary, which is required for making decisions. Then what comes from the business applications, so like all this ERP, SCM, etc., is there's a manual data capture today, which happens in the business applications, and that goes through to cloud computing. Now, obviously, you can see a lot of improvement in this also, because all this manual data capture slows down the event capture itself. So if you have any IoT enabled systems which capture this data, or not even IoT, I would say you could have cameras, you could have RFID tags, you could have any other ways of capturing data, but that will make it much faster. And then lastly, you need external data also, because it's not everything that internally the company generates. There are external inputs, like something from customers, something from suppliers, something from transporters, something from testing labs. And you need all that data also to take certain decisions, because some actions are taken outside the premises. Or if your company itself is in a multi-tier manufacturing setup, where it's a B2B kind of setup, where you create some intermediate products and the next unit creates the next level of products, or there's an assembly line and so on and so forth, then this could be called as external data for that factory unit. So again, you need cloud computing for that when you want to connect multiple locations together. So that's what it is about. The current challenges, if you ask me, are these: that most of the companies have ERP systems and some have IoT enabled data capture. This is answering one of the questions which was asked, that where is India today? So yes, I would say most of the companies have ERP and IoT enabled data capture to some extent. IoT data is at best integrated with robotics for automatic applications, or using edge computer applications, and in some places IoT data is not well integrated with ERP, SCM, and other business applications, because they are the two pillars, as we saw. And historically, there has been a different way of looking at these pillars as different technologies. Hence, they don't integrate. And there's a great need of integrating them together. Then most of the data required for these applications is entered manually, or it is captured by mobile RFID scanners and so on, but not through IoT. So there is a big gap between IoT data and this data. These are two different input streams, and ERP systems don't take IoT data so fast today. Then there are very few companies which use any decision systems that are automated using AI and ML, that is artificial intelligence or machine learning applications. And most of them are in pilot mode today or experimenting with it. Then AR, VR, that is augmented reality, virtual reality, is rarely used in factory simulations. And that is another thing that they can definitely look at to get ahead. Typically today, AR, VR is used for marketing and for product presentations and some canned demos and for training sometimes. So that's what I would say. So digital factory still remains a distant dream for most of the companies in India today. They are somewhere there. I would say the business application pillar is like 75-80% there. IoT pillar maybe 50% there, and the other third pillar of decision making using AI ML might be 10%. So that's the level of completion of the three pillars. And if you want to have Industry 4.0 running on top of these, all these three pillars need to be almost 100% complete. So that's how we can put it as a simple way. So how to go next after this? So if let us say we understand now that these are the technologies to be learned and this is to be done, and finally we need to reach a digital twin. That is our aim or the final goal. So how to go about it? Since again I am interested in creating online training contents for this, and I conduct a lot of training sessions, I suggest the participants to follow this approach, that you do on demand learning. That is, don't try to learn all these 10 technologies together just for the sake of learning. You learn them as and when required and to the required extent. And you could have a team of people working in the organization who work together on these technologies, because one may not be expert in all these together. You might understand it to some level, but there might be other people who are expert at implementing it. So you need to start at project level, do a project, and all the technologies required to implement that project, try to see where to get that talent and expertise. I have talked to some of these companies, and I find that most of the companies say that the biggest problem is the talent required on these technologies. So you see that there's so much demand for these technologies, and if you learn these technologies, you don't have to go and hunting for jobs. Jobs will come hunting toward you. Like, yeah, we need you. So that's one approach. Other approach is to be a jack of all and not a master of one. So either you can focus on some technologies and be expert in them, or you could be the system integrator, because integration is also a big challenge today. That if there are 10 different technologies, they don't talk to each other, they don't know how to integrate with each other. And some of the videos that we saw from Siemens, that really talks. You see the way that video, the first one, if you saw, it says that the bottle that is created has a label on it, which has these QR codes, etc., which tells what is the cap to be fit on this bottle, what is the liquid to be filled in this bottle, and what is the label to be put on this bottle also. So the bottle is the one which tells the machine that what is to be done with me. And that is the approach we have to really adopt. It's not that people are trying to tell what to fill in this bottle to the machine, but the bottle itself is saying that I am so and so. That is what is known as a service oriented architecture. If you look at the 2004-5, because I was in IBM that time, and service oriented architecture was there, which says that it's like in software, we have those functions, and it says that, yeah, these are the inputs you give me, and this is the output I give you. And it's not that you have to document it elsewhere. The first thing you have to ask is, you have to ask that function, what do you do? And it can tell you what it does. Then you have to ask the function, okay, what do you need as inputs for this? It tells you this is what I need as input, and that's how it works. So you don't have to ask a third person that how does this function work. And they are saying that for every small object and piece also, it should have this own coded information on it, which you can be tapping through some APIs. And this is a very interesting concept, that how things can be smart objects on their own. For example, if there's a nut bolt which has to go and fit in the vehicle, then the nut bolt must have a QR code or something which the computer can read and say, oh, by the way, this I go and fit in this place. So that's how it can show you in virtual reality that if you pick me up, if I just pick up a nut bolt and say, where do I fit this in a car? I should have a virtual reality tool or an augmented reality tool, which you saw in that video also. It shows that this nut, fix it in this place. So that's it. You don't have to understand what is to be done with this, and nobody tells you. You just pick up the nut and nut bolt, and that will tell you where to put. So that is what is digital, or I would say that is the way objects need to be created. And interestingly, I was talking to Dr. Joshi from IIT Bombay Electronics Department. He is heading the Industry 4.0 initiative at IIT Bombay. He said we are working on two major things. One is on this, what you say, self-identifiable objects and the standards and protocols to be used, so that through APIs you can try to talk to these objects. So that's the work IIT Bombay is doing right now. They said that for all this integration to happen, you have to have a lot of standards and protocols developed, which are still missing today. If you look at Siemens, if you look at Bosch, they have their own protocols, but those are all proprietary protocols. So they say this is not a very good idea. And then you have to use their own tools, because their tools understand their protocols and their QR codes and everything, but it's not open source. And IIT Bombay is trying to see that how it can be de-linked from Siemens technology or Bosch technology or IBM technology and so on. So that's an interesting area to look at. Okay, lastly, we will come to the digital twins, which lays down a clear vision of how an automated factory works. So this is another interesting way to look at things. There are multiple videos on this from IBM, from Siemens, from Azure. Everybody is trying to get into this space now because that's a new thing coming up. But I would not like to get into all those videos. I will show you a slightly different video from GE. But let us first understand what are digital twins and then see how they are implemented in real life today. that we'll see in the video. So digital twin refer to a digital replica of the physical assets that you have in the plant or in the factory. So it includes people, processes, places, system, devices, everything, and you create a replica of that on a soft copy, or it's like a virtual gaming, you can call it, or you can call it a virtual reality or whatever you want to call it. All the elements, including the dynamics, are represented in this. So you can look at a computer and see what's happening in the factory, or you can also use it to direct to what is to be done next. So both the things are possible. So it reflects what is happening in the factory as of now, and you can give it commands to say what is to happen next. So that's what is a digital twin. And what you do here is actually implemented in the factory, in the shop floor. So from our aspect, if you look at the data aspect of digital twins, because our focus is on the data centric view. So there are three important things to look at. One is device data collection around IoT devices. So you need to have an IoT setup and data interfaces defined so that all the data gets collected for the data foundation. You need to have better data analysis of it, the cognitive computing on the data that is generated, for which you need big data, business analytics, and so on. And lastly, you need better operations to be done using this data and the decisions that are taken in these analytics models. So it is designed. So what is the design versus actual one? And this is the corrective mechanism, I would say, where dynamically you recalibrate based on what is actually happening on the shop floor through the insights. So it's not saying that you make a plan and say that start doing this and then you don't know what's happening really. Every point, every step, you know what happened really, and accordingly the plan can change. Just to give you a simple example of this digital twin, if you're driving on the road using a Google map, that's what it is. So if the Google map tells you turn left and you take this road and you actually don't do that, you take some other road and you go in some different way, then the map recalibrates automatically and then starts telling you, by the way, now if you want to go reach your same destination, then this is the new road to take and this is the new way to go. So you know that every time it recalibrates and starts telling you. So it's not like once you set a map and then if you don't follow the map, then you don't know where you are and where the map is. No, it's not like that. The map dynamically keeps changing as per where you are. And that's how that similarly, the digital twin software should dynamically keep changing depending on what's happening on the shop floor and keep telling you that, by the way, now this has happened, so do this. Now this has happened, so do this. And this is a back and forth mechanism which you can easily observe in our Google Maps today, the way you drive. So that's an example I can say. This digital twins, there are tools available from Siemens like Team Center. That's one of the tools available today. It has several modules. And what this does overall is it creates a complete digital process of design, planning, plant layout, and then process validation, throughput optimization, and execution. So it's almost the entire factory gets mapped through Team Center as a tool. So let us see what is the effect of these kind of tools. And we'll see a video from GE Electric that how this Siemens tool and GE Electric have worked wonders in creating this kind of action in the shop floor. So this is really a vision come true, you can say. And this video, I think, again, is from 2018 or something. So just let's see that video and then I will take a break. And then maybe we can go back to our question answer session after that. Yeah, I hope it's visible and audible. It's about 14 minutes, so I might skip some parts of it, just in the interest of time.
Operator, a change in my mission is causing damage to my HP turbine rotor.
Hey, Twin, help me understand the problem. What's your operating profile?
In past 6 months, my number of cold starts is 4, my number of warm starts is 8, my number of hot starts is 39. The number of start-stop cycles has increased by 27.5%.
Twin, tell me about your rotor damage.
My damage rate has increased by 4.0 times over last 6 months. If this continues, I would lose 69.9% of my useful life.
Twin, give me options for mitigating that rotor damage.
Based on weather forecasts, historical data, fuel cost, electricity pricing in my present condition, I have 2 options for you to optimize operations. Option 1 is to manually slow down my startup ramp rate so that you can reduce the wear on my rotor. Option 2 is to download the Opflex app and apply stress controls to minimize wear and reduce fuel consumption too.
Twin, give me the factors you use to calculate options.
I used my past 15 years of historical data, fleet learning from 125 other D11 steam turbines like me, and 58,965 simulation runs to get this recommendation. I'm 95% confident of my assumptions.
Twin, I need a financial perspective. Tell me about the numbers.
The numbers look good. We can reduce stress by 25%, which brings the damage rate back to normal range. Startup fuel cost will go down by 40% and startup time will be cut by 50%. You will also avoid $12 million by preventing an unplanned outage.
Twin, okay. I select option 2. Let's do it.
I'm initiating option 2, which is Flex Start. Thank you.
Okay, good morning. What you saw just now was not a glimpse into the future. This is happening now, today. This is a representation of a D11 steam turbine that's currently running in Southern California. We call these representations digital twins. What you saw was an example of the human mind working with the mind of our machines. What's a digital twin? It's a living model that drives a business outcome. So this model gets data, gets operational data and environmental data, and constantly updates itself. It also can reach into the fleet, the 125 D11 turbines, and it acquires knowledge from them and learning from them, and it incorporates this into the model. And it uses this to drive business outcomes. It can drive outcomes like it can predict, or it can warn us and then predict failures to reduce maintenance costs and unplanned outages. It can give us the ability to optimize or provide mitigation events when we find out that we have these type of failures. And it can also allow us to forecast opportunities and actually benefit from these opportunities. So let me step back and actually walk you through what occurred in this digital twin in a very simplified way. So when you think about the twin, it really operates in 3 stages: see, think, and do. So in the seeing stage, and I'll relate this to what you saw previously, in the seeing stage, what it's doing, it's actually gathering data of its situation to give you a warning or prediction. This data that comes in is both operational data and environmental data. Operational data like the steam temperatures, the bowl temperatures, the rotor speeds. It takes that data and it uses a model, that living model. This is a hybrid model of physical and digital capabilities. So it's a combination of metal fatigue, metal creep, Bayesian learning, and other machine learning techniques. And it uses this to create a cumulative damage understanding of what's happening on that rotor. As it does that, when it hits a threshold, it can then warn us there's a problem. It then can actually predict the problem. It also uses similarity learning techniques to reach into that fleet of 125 other D11s and gather their knowledge as well. So this is a model that's constantly updating itself to reflect the precise conditions of the asset and then learning from others in the fleet. After after it does that, it has the ability to give us these insights at the right time. That's the first stage. And it does that through APM and using the digital thread to get all that data. The second stage is the think stage. This is when I asked the twin to give me options that I could pursue. To do that, it ran simulations, over 58,000 simulations, running them on the Predix platform, as Harel described in the cloud, on those edge boxes. It's looking at historical data, it's looking at fleet data, it's looking at lifing models, it's looking at forecasts for revenue and cost, and it's giving you a number of options. It then reasons across the option based upon the risk and confidence that it can deliver. And with that, it delivered us two options. One that was manual, and one that could be delivered by an application that would run on a control system on the edge, exactly as described before. Now we get to the do stage. The do stage is all about informing us and executing what needs to be done. So in option one, in the manual option, what you could do is you can have it prescribed to you. What's the load rates, the ramp rates, the steam temperature that's needed for an operator to actually manually input. And all that is logged in APM and delivered to an operator to manually input. Or you can use an app downloaded to the edge, running analytics on the edge, one of those boxes you saw previously. Now that app can run much more precisely. It can precisely monitor the load and the ramp rates, aligning it with the steam temperature so that the thermal stresses on the rotor are minimal. That's how you get to that 25% reduction number. It also, by doing that, allows you to start a lot faster and burn less fuel. That's where you see the other benefits show up. All of this executing on an edge device. That's see, think, and do. These are the digital twins working with us, with the minds of the machines, creating these capabilities. Now, what if I wanted to go in a much more immersive environment and have the twin help me understand the problem? How about I use one of these Microsoft HoloLens, which I suddenly found here. So what I'm going to do is I'm actually going to use this lens to get a much more immersive environment. So what we would normally do is we would normally go into the actual physical plant and look at the steam turbine itself, the physical steam turbine. And from that physical steam turbine, what I would do there, let's make sure we get this to do right. What I would do there is I would overlay all of my digital capabilities on the physical asset, seeing exactly where the damage was occurring. Now, as I can't do that, I can't take us all on that journey 6 hours away. What I'll do is I'll ask the twin to bring that to us, take the exact CAD dimensions of the asset from manufacturing and maintenance, and simulate it in this environment. Right? Now, as it begins to do that, you'll see the steam turbine appear. And it should be appearing any second now. Or is it one of these usual glitches when you do these things that you see appearing? All right, might be a glitch. There it is, in the audience. Now I can have the twin help me. Twin, open the steam turbine. Okay, that didn't work. Twin, open the steam turbine. Let's see if that works better. Let's use the hand gesture. Okay, give it a second here. Okay. Twin, show me where the wear is twin. Show me the length of the wear and plot a baseline for me so I can see if we did no mitigation, what that would be. Okay, twin, close the steam turbine. This thing is still floating around. What you saw there was an experience of one of 551,000 digital twins that we have currently running. This one can communicate with us in a richness of voice and vision that is usually unbelievable, but quite real. But all of them deliver value. Several of them deliver value in different ways. So what you've seen here is a list of the other twins that we have. So we have parts twins, which is what you just saw, the rotor failure prediction. And this parts twin, what that can do, just like we saw, is deliver an early warning about a problem, as well as tell you about the actual failure that you'll encounter. We have product twins. What product twins do is they actually optimize the remaining life of a steam turbine or any asset, and they do it against maintenance costs. What process twins do is they find ways to optimize scheduling of field engineers, in this example, to maximize the utilization. What the system twins do is the system twins find a way to actually optimize against a multiplicity of KPIs, balancing things like revenue against remaining life against maintenance costs. All of these twins providing value. So when you think about the era that we're going into of emergence, this is the era in which we have the minds of the humans, maybe 6 billion of them, talking to the minds of the machines, 50 billion of them. That convergence is going to profoundly change everything we know. We believe with the power that we have in Predix, the thread, the twin, and APM, we are perfectly suited with our partners and our customers to move to the next space. Thank you very much for your time, and my thanks to the twin.
Okay, with that, we come almost to the end of our session. Maybe 1 or 2 slides, and then if you have any more questions, let me know. Yeah, that's it. Thank you.
Any questions, anyone? Maybe you can unmute yourself.
Yeah.
And
Yeah, I was wondering after listening to all this about the initial capital investment that would be needed. So basically, you look at your manufacturing from a global perspective rather than from a local perspective, and therefore, companies which are far ahead in this in manufacturing could be manufacturing for the world, and the Indian, maybe manufacturing will have to take place abroad. Although you might develop software for them. But then it will have to take place abroad, and then India will be a huge market rather than developer of any kind of technology. So that is the one risk I perceive. Maybe I'm wrong, but then that seems to be a possibility.
Yeah, Prashant, I agree with you. Maybe others can have their opinion on this, because this is a topic on which people can have different opinions.
Hi, Pradeep here, Atul.
Yeah, sure. Good.
I have written a question in chat. Is there some protocol being developed combining all the three pillars as such? Because there are several companies with their own what we call intellectual properties, and they are not ready to communicate with each other. And every one of them has a strong presence in something, like SAP is in ERP, mostly in that is, yeah.
So there are attempts to create open source for this, and that is where I said IIT Bombay is one of the institutes I know who is leading in this effort. So Dr. Joshi at IIT Bombay Electronics Department is the head. And in case you want to know more of what exactly they are doing, maybe we can talk to them. So they are trying to build those open protocols for connecting all these devices.
Because this is going to be a very vast and big and all-encompassing, as we say.
Yes.
And there will be one German solution, there will be some American solution, and we will be caught in between somewhere or something like that is what I foresee in this.
Very true. Today, Siemens solutions are more proprietary because Siemens has a team center solution, Bosch has their own solutions, IBM has their own solutions, and they are different.
Yeah.
In fact, Pradeep, to put in something to your, see, as Ford had said earlier, that if you don't develop technology, you will pay for it without having it. So that is what will happen to India if we don't develop our own technology. I mean, we have been importing from all over the place. So that culture will have to stop. Germany cannot import from place, Japan cannot import from others. So that and unless they develop technology, we cannot hope to get any technology. That is the state of affairs today.
Yeah, true.
So, any idea about what is the size of IoT or IIoT presently, like in the terms of maybe some numbers, number of sensors or number of households using that, some instruments which have been connected?
No, right now, if you ask me,
like we know the internet users.
Yeah, see, if you ask me today, there are these consumer goods companies like LG and GE Electric. So they are trying to put some IoT devices on their washing machines, refrigerators, which are connected to the internet through your home. And if there is a problem, they automatically come to know, and they're trying out some of those things. So, but the numbers wise, I won't have any idea of how many of those. It's like there will be a few billions. Like in the video, they are saying that there are 6 billion people and there will be 55 billion IoT machines or IoT connected devices in the world in the coming few years.
Okay.
And I was talking to another friend who is my NITI alumni. He leads ICANN organization in the world, which is the the Internet Address Organization of the world. So he was also telling me the same thing, that originally the 6-digit internet addresses, and now they are expanding a bit more. They are saying that no, this six pieces of digital ID will not work if you really connect so many machines in the world, because earlier they were thinking of only people connecting on the internet. So their target was like 10 billion. But with machines, they are saying it will easily go to more than 100 billion. And each machine has to be identified as an individual, just like we identify our machines and laptops. So all these small machines, like 100 billion devices, will be on the internet. And they are looking at what is the next internet address space and what they can create to accommodate so many of them.
So now coming to again Pradeep's question, I mean, what Pradeep asked, would you need some new languages, programming languages, so that there can be machine-to-machine communication, product-to-machine communication, and communication among fixtures and tools and so on. So, I mean, once whatever languages we have today, the so-called high-level languages, may not be suitable for any of these things. So maybe you can comment on the development of new languages, new compilers, and so on.
Yeah, personally, I'm not an expert on those, but yes, I think those already exist. So it's not like those languages are not there. They are more proprietary. Now, which language will pick up and which will not pick up, I don't know. And if there are open source organizations which start working on this, it will work better. And IIT Bombay is looking at that. That's one I know. Now, which languages they are looking at and which other organizations in the world they are connecting to, etc., is something I don't know right now.
So is this the person from IIT Bombay, Joshi? Is it Suhas Joshi or some or?
Yeah, I think Dr. Suhas Joshi. He is head of
Suhas Joshi
electronics
is
department.
mechanical department because I don't know anybody from He's a dean of alumni and corporate relations. So.
No. I think the person is from electronics department, not mechanical for sure.
Okay.
But anyway,
Then maybe somebody else then.
Yeah,
okay, I'll find out. Yeah.
But yes, what you're saying is correct. We need to define those standard protocols, languages, interfaces, and if it's an open source, then everybody can start using it. Otherwise, it becomes proprietary.
Correct.
So I think it's 6:30. So thank you, Atul. Thank you very much from this group. I am a manufacturing person, and I can see an onslaught of Industry 4.0, particularly through your two videos, what you shared as such. And if it is going to be cheaper, faster, better, we knew this when mass manufacturing came into picture. But that one more thing which you taught us is also it is customized as per your wish.
Yes.
Both the videos were really eye-opening. That is, the bottle itself telling me, okay, what should be filled in me, and machine understanding it. It's something unique.
Yes.
And what I see is we cannot hide from it. There is no way we can hide. Either we get a part of it, we should be a part of it and start working on it, or just get imported material and use it and be a consumer. I think this group is promoting to be the first part. That is, let us be on this journey together, and with help of your insight and your study, I think definitely we should work and we should try for it. There is no stopping of Industry 4.0 is what I can understand, I could see from your presentation. Thanks for sharing. It was a wonderful सगळ्यांना समजेल अशा भाषेतलं आणि असं होतं. So let's try and get on this bandwagon is what I would say to the group. And thank you very much once again from the group side. It has been a good series, eye-opening series, excellent series, and something we can do असे promote करणारी series आहे असं मला वाटतं. Once again, thank you very much.
Thank you, sir.